Hi students, in this video we are going to talk about the concept of conditional probability. See, the probabilities get modified when we have some partial information about outcome. For example, let us consider a random experiment of rolling a fair die. When we roll a die, there are 6 possible outcomes, right? So the sample space will be set consisting of 1, 2, 3, 4, 5, 6. Let us be interested in following events A, B, C. Here A is the event, the die landing on prime number. B be the event, the die landing on even number. C be the event, the die landing on odd number. Okay, it's clearly the probability of A going to be 3 by 6, which is going to be 1 by 2. Okay, now intuitively, what should be the probability of A given that B already happened? See, when we have information that B already happened, we only think of 2, 4, 6 as a possible outcome, right? That means B kind of become now a new reduced sample space. Okay? And out of 2, 4, 6, only 2 is favorable for being prime. So that's why the probability of A given that B already happened should be equal to 1 by 3. And this is not equal to probability of A, which is 1 by 2. So now when we have information that B already happened, the probability of A reduced to 1 by 3 from 1 by 2. Similarly, probability of A given that C already happened will be 2 by 3, because when we know that C already happened, we only think of 1, 3, 5 as a possible outcomes. Now the C kind of become new reduced sample space. Out of 1, 3, 5, 3 and 5 are favorable for being prime. So that's why the probability of A given that C already happened should be 2 by 3, again which is not equal to 1 by 2. This time when we have information that C already happened, the probability of A increased to 2 by 3 from 1 by 2. So from this experience, we understand that we might have to update probability of an event when we have some partial information about outcome. Question is, how to update probability of an event using partial information? To get an intuition, let us consider a random experiment whose sample space is finite and outcomes are equally likely. Let omega be the sample space and A and B are two events. Say we are interested in determining probability of A when we know that B already happened. So when we know B already happened, B become our new reduced sample space, and only outcomes of A that concern us are those, if any, that are also outcomes from B, means outcomes from A intersection B. So it makes sense to define the probability of A given that B already happened as number of elements in A intersection B by number of elements in B. Okay. Now let us try to express this probability in terms of our original probabilities. For that, let us divide numerator and denominator by number of elements in omega. Okay, then the numerator is nothing but probability of A intersection B. This denominator is nothing but probability of B. So we got this updating rule. The probability of A given that B already happened, we are updating as probability of A intersection B by probability of B. Okay, fine. Now first let us check if this updating rule is consistent with the intuitive probabilities that we obtained for our above die example. Okay, so in the above die example, the probability of A given that B happened, So according to this updating rule, we have to take as probability of A intersection B by probability of B. But what is A intersection B? A intersection B is the even prime. It will be 2. So the probability of singleton 2 going to be 1 by 6. So that's why the probability of A intersection be 1 by 6 and probability of even is 1 by 2. So 1 by 6 by 1 by 2 going to be 1 by 3. So fine. Next, similarly, the probability of A given that C happened, according to this updating rule, it should be probability of A intersection C by probability of C, and A intersection C means odd prime, which is 3 and 5. So 2 are favorable out of 6, so it should be 1 by 3, and probability of C, probability of die landing on odd number, which is 1 by 2. So 1 by 3 by 1 by 2 going to be 2 by 3. So this updating rule is consistent with our intuitive probabilities for above die example. Now let us check mathematically. This updating rule is indeed a probability measure. Okay. Let this triple omega script of P be a probability space and B be an event with positive probability. Now we are going to define an updated probability function with respect to the information that B already happened. Okay, we define a set function P sub B. It's a function from event space to real number defined like this. P of A equal to P of A intersection B by P of B for all A in event space. Okay, here this P is our original probability function. Okay, now we are going to show that this updating rule of PB is indeed a valid probability measure. For that, we need to verify three axioms of probability: axiom 1, axiom 2, and axiom 3. Okay, the claim PB is a probability measure. Okay, we are going to check three axioms one by one. Axiom 1, non-negativity. Axiom 2, certainty. Axiom 3, countable additivity. First, let us verify axiom 1. For that, we need to show that PB of A is non-negative for all A in event space. Okay. Now, PB of A, according to updating rule, which is P of A intersection B by P of B. But P already a probability measure, right? So, the numerator is non-negative, denominator is non-negative by axiom 1 for P. So, the whole thing is going to be non-negative. So we can say that PB of A is non-negative for all A in event space. Therefore, we just verified axiom 1. Axiom 1 is fine for PB. Next, we go for axiom 2. Certainty axiom. PB of omega, according to updating rule, P of omega intersection B by P of B. But omega intersection B is going to be same as B. Therefore, here the numerator is simply P of B by P of B. P of B positive, so it will give you 1. So, we just verified axiom 2 for PB. Okay. Now let us verify axiom 3. Let A1, A2, A3, so on, AN are countable collection of mutually exclusive events in event space. Then we need to show that PB of union I equal to 1 to infinity AI, same as summation I equal to 1 to infinity PB of AI. Okay, if you can show this, then axiom 3 is verified. Okay, here let us start with a PB of union I equal to 1 to infinity AI. According to updating rule, this is going to be P of union I equal to 1 to infinity AI intersecting with B by P of B. Now, this union I equal to 1 to infinity AI intersecting with B, we can write union I equal to 1 to infinity AI intersecting with B due to generalized version of distributive laws. So the next step, this part is replaced with this one due to generalized version of distributive laws. Okay. Now here A1, A2, A3, so on, An, which are mutually exclusive events. So A1 intersection B, A2 intersection B, so on, An intersection B. This countable collection also going to be mutually exclusive. Here we can apply axiom 3 for P. So we can write summation I equal to 1 to infinity P of A intersection B, because P is already probability measure. So we have axiom 3 for P. So therefore the next step we are writing this numerator as summation I equal to 1 to infinity P of A intersection B, because A1 intersection B, A2 intersection B, so on. These are again mutually exclusive collection of events, and we have axiom 3 for P. Now if we rewrite this summation, we can write summation I equal to 1 to infinity P of A intersection B by P of B. Now this is exactly equal to PP of AI according to our updating rule. So therefore we have PP of union I equal to 1 to infinity AI equal to summation I equal to 1 to infinity PP of AI. So therefore axiom 3 is verified. Okay. So now we can say that PP is a valid probability measure. Okay, fine. Next, for any event A in event space, this PB of A is called conditional probability of A given that B already happened. Okay, in practice, this PB of A is denoted by this, and we read it as probability of A given B. Okay, and the probability of A given B now what? P of A intersection B by P of B. It makes sense when P of B positive, because we don't want denominator to be 0. Okay. So this is a conditional probability definition. So this is how we update probability of an event when you know that some event already happened. Okay. This is a definition for conditional probability of A given that B already happened. Next. Example 1. A family has two children. What is the conditional probability that both are boys given that question 1, family has a boy. Question 2, given that elder one is boy. These two are actually different. First of all, family has two children. So what is the sample space? How do we describe outcomes here? We are describing like this: order pair B comma B means elder one is boy, younger one is boy. Order pair B comma G means elder one is boy, younger one is girl. And here elder one is girl, younger one is boy. Both are girls. Okay, fine. So this is the sample space. Now, let us say A be the event that family having both boys. Okay, that means A consisting of only single outcome B comma P. That implies probability of A going to be what? 1 by 4. Out of these 4, only boy comma boy is favorable. So obviously the probability of A is 1 by 4. Let B be the event that family having a boy, at least one boy. So that means these three are favorable to B. Family should have a boy, right? Only outcome that is not favorable to B is order pair G comma G. Okay. So that therefore Here B having 3 outcomes favorable to B, so the probability of B going to be 3 by 4. C be the event that family having elder one boy. So in C, there are two outcomes here. We want elder one to be boy, younger one can be either boy or girl. So we have a two outcomes here, B comma B, B comma G. Okay. So therefore the probability of C going to be 2 by 4, which will be 1 by 2. Okay. Now question 1. In question 1, we are interested in conditional probability. The probability of A given that B, okay, because conditional probability of both boys given that family has a boy, given that B happened, right? In second question, we are interested in probability of A given that C happened, okay. Now let us do this. Now probability of A given B, according to conditional probability definition, probability of A intersection B by probability of B. See, A intersection B going to be same as A because A is actually subset of B, okay, which is same as probability of A. Probability of A we already got 1 by 4, so 1 by 4, and probability of B also we got 3 by 4, 1 by 4 by 3 by 4 going to be 1 by 3. So conditional probability of this A given B going to be 1 by 3. Now question 2. Conditional probability of A given C. According to conditional probability definition, this is probability of A intersection C by probability of C. Again, A is also subset of C, that implies A intersection C will be same as A. That's why this is same as probability of A. So numerator is going to be 1 by 4, which is probability of A, and probability of C, we have seen that is 1 by 2. So now 1 by 4 by 1 by 2 going to be 1 by 2. Okay. Now we see that the conditional probability of family having both boys given that family as a boy is 1 by 3, and conditional probability of family having both boys given that elder one is boy is 1 by 2. Okay. Here most people approach first one as a second one and come up with the answer 1 by 2. But please understand these two questions are different. Okay. Example 2. In an exam, two reasoning problems 1 and 2 are asked. 35% students solve the problem 1 and 15% students solve both the problems. What is the probability that student who solve the first problem will also solve the second one? Okay, solution here. Let EI denote the event that students solve the problem I for I equal to 1 and 2. There are two events here. E1 denote the event that students solve the problem 1. E2 denote the event that students solve the problem 2. Okay. Here the probability of E1 is given 0.35 because 35% students solve the problem 1. Okay. And 15% students solve both the problems. So the probability of E1 intersection E2 given as 0.15. Here we are interested in probability of E2 given E1. Okay. According to conditional probability definition, probability of E2 given E1 is what? The probability of E2 intersection E1 by probability of E1, but E1 intersection E2 same as E2 intersection E1 because of commutative property of this intersection. So this is going to be 0.15 by 0.35. Okay, so that's what probability of E2 given E1 equal to probability of E1 intersection E2 by probability of E1. So probability of E1 intersection E2 0.15, probability of E1 0.35. So this gets simplified to 0.428 approximately. Okay, next. Multiplication theorem. Multiplication theorem. Here is the statement. Theorem. Let omega script of P be a probability space and A and B are two events in event space with probability of A positive and probability of B positive. Then probability of A intersection B equal to probability of A times probability of B given A, which is also equal to probability of B times probability of A given B. This result directly follow from conditional probability definition. Okay, proof. First, if we consider probability of A given that B happened, probability of A given B, by definition we can write probability of A intersection B by probability of B. If you multiply probability of B both sides, then we will end up with this result. Probability of A intersection B equal to probability of B times probability of A given B. Similarly, if we consider probability of B given that A happened, then according to conditional probability definition, probability of B intersection A by probability of A and B intersection A is same as A intersection B. So anyway, if we multiply probability of A both sides, then we will end up with this result. Probability of A intersection B also probability of A times probability of B given A. So therefore, we got this result. Here, probability of A intersection B, maybe you can write like this: probability of A times probability of B given A by conditioning on A, or you can also write like this: probability of B times probability of A given B by conditioning on B. Okay, you can use whichever you like. Okay, next. Corollary. This is going to be multiplication theorem for three events. In the previous theorem, we considered multiplication theorem for two events. This actually follows from previous theorem. Okay. Here is the statement. If A, B, C are three events in event space with probability of A intersection B positive, then probability of A intersection B intersection C equal to probability of A times probability of B given A times probability of C given A intersection B. Okay, here is the proof. Let's consider probability of A intersection B intersection C. Here we are going to see this A intersection B intersection C as intersection of two events, A intersection B and C. Okay, so A intersection B one event, C the one event. Now let us apply multiplication theorem for two events, A intersection B and C. So we can write probability of A intersection B times probability of C given A intersection B. Multiplication theorem for two events, A intersection B and C. Now let's again apply multiplication theorem for A intersection B here. Okay. Now in the next step we can replace probability of A intersection B with probability of A times probability of B given A. Okay. So now we are done. Okay. So therefore probability of A intersection B intersection C equal to, we have probability of A times probability of B given A times probability of C given A intersection B. This is the multiplication theorem for three events. Okay. Now let's do a problem. Example 3. Example. Suppose an urn contains 7 black balls and 5 white balls. We draw 2 balls from the urn without replacement at random. What is the probability that the both drawn balls are black? Okay. Here, what is the random experiment? We draw 2 balls from urn containing 7 black and 5 white balls. So the total number of possible outcomes is going to be 12 choose 2, because we can pick any 2 balls from 7 plus 5, 12 balls. So the sample space size is going to be, the number of elements in omega are going to be 12 choose 2, which is going to be 66. Let E be the event that both selected balls are black. Okay, how many ways this E can happen? If you want both balls to be black, you can pick any two from 7 black balls. So the number of elements in E going to be 7 choose 2, which is 21. Now we can use classical definition of probability because we are picking these two balls at random. So we can assume outcomes are equally likely. So the probability of E going to be number of elements in E by number of elements in omega, which is 21 by 66. This is same as 7 by 22. Fine. Okay. This is the answer, 7 by 22. There is another approach to answer this question using multiplication theorem. Okay, let me show you. Let E1 denote the event that first drawn ball is black. E2 denote the event that second drawn ball is black. Then our event of interest is going to be E1 intersection E2. We want both to be blacks, right? Okay. Then our event of interest E can be expressed in terms of E1 and E2 like this. E1 intersection E2. Okay. Now we are interested in probability of E1 intersection E2. Now the probability of E1 equal to 7 by 12. The probability of the first drawn ball is black is going to be 7 by 12 because initially there are 12 balls in which 7 are black. So obviously the probability of E1 going to be 7 by 12. Now the conditional probability of E2 given that E1 happened is going to be 6 by 11. When you are drawing the second ball, in the arm there are only 11 balls in which there are only 6 black balls because one black ball already withdrawn in the first draw. So that's why 6 by 11 is the conditional probability of E2 given E1. Now the probability of E1 intersection E2, according to multiplication theorem, we can write probability of E1 times probability of E2 given E1 by conditioning on E1. Now we know these two probabilities. If we plug it here, 7 by 12 times 6 by 11, which is going to be 7 by 22. Again, we end up with the same answer. So you can also think this way. Generalized multiplication theorem. Here is the statement. Let E1, E2, so on, En are n events in event space with probability of intersection I equal to 1 to n minus 1, Ei is positive. Then the probability of intersection I equal to 1 to n Ei equal to probability of E1 times probability of E2 given that E1 happened times probability of E3 given that E1 and E2 happened times so on probability of En given that E1, E2 so on up to En minus 1 happened. Okay, so this is a statement, generalized multiplication theorem. Here the proof is by induction. You can try. Here you can use base case n equal to 2 that we already proved. Okay, fine. Now let us consider a random experiment of picking a card from well shuffled pack of 52 cards. Okay. Let A be the event of picking a king. Then probability of A going to be 1 by 13 because there are 4 kings, right? So 4 by total 52 cards. Sample space size is going to be 52 when you pick one card. So it's going to be 1 by 13. So the probability of A going to be 1 by 13. Now let us say B be the event of picking heart. Okay, there are 13 hearts, right? So the probability of B going to be 13 by 52, which is going to be 1 by 4. So the probability of B going to be 1 by 4. Now the probability of A intersection B will be 1 by 52 because there is only one king of hearts, right? So that's why 1 by 52 is the probability of A intersection B. Fine. The conditional probability of A given B. The probability of picking king given that it is heart according to conditional probability definition. The probability of A intersection B by probability of B, and we already realized that the probability of A intersection B is 1 by 52 and probability of B is 1 by 4. So 1 by 52 by 1 by 4 is going to be 1 by 13. Okay, and this conditional probability of A given B exactly same as the probability of A, which is 1 by 13. See, we try to update the probability of an event A knowing that B happened, but it didn't get updated. Here the situation is the information about the event B is independent of event A. This leads to the concept of independent events. Let's come up with a definition for independent of two events. Okay. Now, the situation should be like this. Probability of A given B equal to probability of A. Then we want to think like the information about event B is independent of event A. Then we want to say A and B are independent. Okay. Now I want to come up with definition for independence of two events. Okay. Why can't we simply take this as a definition? Probability of, if probability of A given B equal to probability of A, then A and B are independent. Okay. See, this expression makes sense only when probability of B positive, because when you are saying that probability of A given B, then you are talking about this expression probability of A intersection B by probability of B. Okay, you are keeping probability of B in the denominator, so that's why this expression makes sense only when probability of B positive. We don't want to have such a limitation. That's why what we do, if you multiply this probability of B this side, let me do it in next slide. See now, so we know that when probability of B positive, this expression makes sense. Then what is the probability of A given B? According to conditional probability definition, the left hand side is probability of A intersection B by probability of B. Now, if you multiply both sides probability of B, now you end up with probability of A intersection B equal to probability of A into probability of B. See, in this expression, there is no problem. Whether probability of B positive or 0, it always makes sense. But in this expression, since probability of B in the denominator, we have a problem to make sense out of this expression, but this expression always meaningful. That's why we are going to take this one as a definition rather than this one. So now we are going to give a definition for independence of two events. Fine. Definition: two events E1, E2 in event space are said to be independent if probability of E1 intersection E2 equal to probability of E1 times probability of E2. This is the definition for independence of two events. Okay. Similarly, we can talk about independence of three events. Three events E1, E2, E3 in event space are said to be independent if probability of E1 intersection E2 equal to probability of E1 into probability of E2. Probability of E2 intersection E3 equal to probability of E2 into probability of E3. Probability of E1 intersection E3 equal to probability of E1 into probability of E3. That means any pair should be independent. E1, E2 should be independent according to the previous definition. E2, E3 should be independent. E1, E3 should be also independent. Okay. Not only this pairs, now we should also want to have this probability of E1 intersection E2 intersection E3 equal to probability of E1 times probability of E2 times probability of E3. Okay. So actually, the probability of E1 intersection E2 intersection E3 in general by multiplication theorem, we have this probability of E1 times probability of E2 given E1 happened times probability of E3 given E1 intersection E2. This is in general by multiplication theorem. But when you believe that E1, E2, E3 are independent, now this probability of E1 as it is, this probability of E2 given E1 should be same as probability of E2 if E1, E2 are independent. And next, And next, the probability of E3 given that E1 and E2 happen should be same as probability of E3 if you believe that E3 is independent of E1 and E2. So we should also have this one. The probability of E1 intersection E2 intersection E3 should be equal to probability of E1 times probability of E2 times probability of E3. If these four conditions are okay, then we say E1, E2, E3 are independent events. Okay, mutually independent. Next. In general, n events E1, E2, so on, En in event space are said to be independent or mutually independent if probability of intersection of every subcollection of E1, E2, En should be equal to product of their probabilities. That is, for every choice of this capital I with size greater than or equal to, where this capital I is subcollection from 1 to n, the probability of intersection of EIs where I varying over this capital I should be product of probability of EIs where I varying over this capital I. Okay, so if this happen with every I which is subset of 1 to n with size greater than or equal to, then we say E1, E2, so on, En are independent. See, here we are checking a lot of conditions. For example, let me write, in the case we have a 4 events, E1, E2, E3, E4. These are said to be independent if probability of EI intersection EJ equal to probability of EI into probability of EJ for all 1 less than or equal to I less than j less than or equal to 4. There are 4 choose 2 like that. Next, probability of EI intersection EJ intersection EK should be equal to probability of EI into probability of EJ into probability of EK for 1 less than or equal to I less than j less than k less than or equal to 4. Then finally 4 at a time, probability of E1 intersection E2 intersection E3 intersection E4 must be probability of E1 into probability of E2 into probability of E3 into probability of E4. Okay, so here there will be 4 choose 3 such a condition, here only 4 choose 4 like that. In general, here we will be checking n choose 2 plus n choose 3 plus so on up to n choose n conditions will be there. Okay, there are in general case when we have n events we will be checking this many conditions. Actually, this also equal to from identity I can write 2 power n minus n choose 0 minus n choose 1. This is going to be 2 power n minus 1 minus n. Okay, so this many conditions will be checking, okay, to decide n events are independent. Okay, this is the general definition for n events to be independent. Okay, next we also have a concept of pairwise independence. We say n events E1, E2, so on, En are said to be pairwise independent if every pair of events are independent. Okay, that means probability of EI intersection EJ equal to probability of EI into probability of EJ for all I not equal j, where I and j from 1 to n. Here there are only n choose 2 conditions to check. Okay, this is a little bit weaker independence. Okay, independence means something stronger. Here we only want any pair to be independent. Okay, this is not same as mutual independence. This is something called pairwise independence. Okay, now obviously independence implies pairwise independence because we also check these conditions in independence and something more, right? But converse may not be true. Okay, I will give an example. Obviously independence implies pairwise independent. By looking at a definition you can tell that. Okay, but converse may not be true. I'm going to give an example. Here is an example. Consider a random experiment of picking a ball at random from the box which contains 4 balls with labels 1, 2, 3, 4. So the sample space here with the 4 outcomes 1, 2, 3, 4. Let us consider 3 events E1, E2, E3, where E1 is the event consisting of 2 outcomes 1 and 2. E2 is the event consisting of 2 outcomes 2 and 3. E3 is the event consisting of 2 outcomes 1 and 3. So here the probability of EI equal to number of elements in EI by number of elements in omega, which is 2 by 4, that equal to 1 by 2 for all I equal to 1, 2, 3. That means probability of E1 1 by 2, probability of E2 1 by 2, probability of E3 also 1 by 2. Now the probability of EI intersection EJ, which is number of elements in EI intersection EJ by number of elements in omega. As you can see, any pair having exactly one outcome common. So this count is 1 for all ij. That's why this probability of EI intersection EJ is going to be 1 by 4 for all I not equal j. Therefore, this probability of EI intersection EJ can be realized as 1 by 2 times 1 by 2. This 1 by 2 we can take as probability of EI. This 1 by 2 we can take as probability of EJ. So the probability of EI intersection EJ same as probability of EI into probability of EJ for all I not equal j. So we have pairwise independence so far. Okay. So that is, we have pairwise independence of E1, E2, E3. Now, to talk about independence, we need to check one more condition. Let's see what happens to that. But the probability of E1 intersection E2 intersection E3 is going to be number of elements in E1 intersection E2 intersection E3 by number of elements in omega, and this count is 0 because we don't have anything common to 3 events. So that's why this intersection is going to be empty. That count is 0. That's why this probability is 0. Obviously, this is not equal to 1 by 8. Probability of E1 into probability of E2 into probability of E3. So we don't have independence, but we still have pairwise independence. Here E1, E2, E3 are not independent, but they are pairwise independence. Here this is an example where E1, E2, E3 are pairwise independent, but they are not independent. So in general, pairwise independence doesn't mean that mutual independence. Theorem: if E1, E2 are independent, then E1, E2 complement also independent. So to show E1, E2 complement independent, we need to show this. Probability of E1 intersection E2 complement equal to probability of E1 times probability of E2 complement. Okay. So what do we know here? E1, E2 are independent. That means we have this. Probability of E1 intersection E2 equal to probability of E1 times probability of E2. We know this, we need to show this. Okay. Now let's start. Proof. Probability of E1 intersection E2 complement equal to probability of E1 minus probability of E1 intersection E2. Okay. We did one theorem in lecture 4. From that I am writing this. Probability of E1 intersection E2 complement equal to probability of E1 minus probability of E1 intersection E2. Okay. Now this probability of E1 intersection E2 can be replaced with this. Next step we'll do that. Probability of E1 minus this one we are replacing with probability of E1 times probability of E2 because E1, E2 are independent. Now if you take probability of E1 common, then probability of E1 times 1 minus probability of E2, and this 1 minus probability of E2 can be seen as probability of E2 complement. So we have this. Okay. Probability of E1 intersection E2 complement equal to probability of E1 times probability of E2 complement. Therefore, we can say E1, E2 complement are independent. Okay, fine. Next, Similarly, we can show that E1, E2 independent implies E1 complement E2 also independent. Pretty similar. Okay. Next theorem. If E1, E2 are independent, then E1 complement E2 complement also independent. Here we need to show this. Probability of E1 complement intersection E2 complement equal to probability of E1 complement times probability of E2 complement. We need to show this. Okay. Okay. Now first let us start with the left hand side. Probability of E1 complement intersection E2 complement. Here from De Morgan laws we can write this one E1 union E2 whole complement. E1 complement intersection E2 complement equal to E1 union E2 whole complement because of De Morgan laws. Okay, De Morgan's law. So now the probability of complement of event is 1 minus probability of an event, right? So therefore probability of this event going to be 1 minus probability of E1 union E2. Okay. Now from addition theorem of probability, this probability of E1 union E2 I can write probability of E1 plus probability of E2 minus probability of E1 intersection E2. Okay. Next step 1 minus the probability of E1 plus probability of E2 minus probability of E1 intersection E2 from addition theorem of probability. Okay. Now, if you multiply minus inside, also use the fact that E1, E2 are independent. So this can be replaced with probability of E1 times probability of E2. Also, we are multiplying minus inside. So we have this. Now here 1 minus probability of E1. From here, if we take minus probability of E2 common, then we have 1 minus probability of E1. Okay, so therefore 1 minus probability of E1 common, then 1 minus probability of E1 times 1 minus probability of E2. Okay, next step I will write that 1 minus probability of E1 times 1 minus probability of E2. This is nothing but probability of E1 complement. This is nothing but probability of E2 complement. So therefore we have it. Okay, probability of E1 complement intersection E2 complement equal to probability of E1 complement times probability of E2 complement. Therefore E1 complement E2 complement are independent. Okay, fine. We have a general statement here. In general, if E1, E2, so on, En are independent, then F1, F2, so on, Fn also independent, where each Fi is either Ei or Ei complement. Okay, so whatever I can make like F1, F2, Fn, keeping Fi is either Ei or Ei complement, all those events will be again independent. Okay, so fine. Next. Theorem. If E1, E2, so on, En are independent events in event space, then the probability of union I equal to 1 to n Ei equal to 1 minus product I equal to 1 to n 1 minus probability of A. See, earlier we used to deal with this probability of this union using inclusion and exclusion principle. We know how bad the formula was. It's so big and we need to know a lot of information. That means we should know the probabilities of all possible intersection of the events to be able to use that tool, right? But here all you need to know is probability of yes, that's all. Then you can compute probability of union I equal to 1 to n A. Okay, but here you should know that events are independent. Okay, you can enjoy this tool only if you know that your events are independent. Otherwise you have to go with inclusion and exclusion principle, and you should know a lot of information to compute the probability of union of EIs using inclusion and exclusion principle. But here, all you need to know is probability of E1, probability of E2, so on, probability of En. Okay, fine. Okay, proof. Let's start with the left hand side. Probability of union I equal to 1 to n EI, I am writing as 1 minus probability of union I equal to 1 to n EI whole complement. Since the probability of any event I can write 1 minus probability of its complement, right? That's why. Now next, this union I equal to 1 to n EI whole complement, by De Morgan laws it is going to be intersection I equal to 1 to n EI complement because of De Morgan laws. Okay, from De Morgan laws this can be replaced with this one. Now if I know E1, E2, so on, En are independent, then I can say that E1 complement, E2 complement, so on, En complement also independent, right? That's why the probability of this intersection going to be product of their probabilities. So I can write 1 minus product I equal to 1 to n probability of EI complement, since independence of E1, E2, so on, En implies independence of E1 complement, E2 complement, so on, En complement. Okay. Now the probability of EI complement is 1 minus probability of EI. So therefore we have this probability of union I equal to 1 to n, EI equal to 1 minus product I equal to 1 to n, 1 minus probability of EI. Okay. This is very handy tool to compute probability of this union when we know E1, E2, so on, En are independent. Okay. Fine. Okay, here is a problem. A problem in probability theory is assigned to 3 students whose names are capital A, capital B and capital C, and they try on their own to solve it. The probabilities of A, B and C solving it are 0.2, 0.3 and 0.5 respectively. Find the probability for problem being solved. Okay. The problem being solved means at least one of A, B, C solving it, right? Okay. Let A denote the event that A solved the problem, B denote the event that B solved the problem, C denote the event that C solved the problem. Okay. Here the probability of A is 0.2, probability of B is 0.3 and probability of C is 0.5. Okay. So we have this. Okay. Now here we are interested in probability of A union B union C. See, our event of interest is expressed in terms of ABC like this. A union B union C means at least one of A, B, C happening. Means at least one of A, B, C solving the problem. That's what we mean by problem being solved. Okay? Okay, fine. Now, here it is very reasonable to assume that A, B, C are independent events as they are trying on their own. That means if one solve the problem will not affect the chances of other solving the problem. Okay, so that's why we can assume that A, B, C are independent, so that we can use above theorem to compute this probability. Okay, we don't have to go for inclusion exclusion principle. Anyway, we don't have enough information to use principle of inclusion exclusion. Okay, so now the probability of A union B union C according to above theorem 1 minus probability of A times 1 minus probability of B times 1 minus probability of C, and we know the probability of A, probability of B, probability of C. Let's plug it here. Then this whole thing gets simplified to 0.72. Therefore, the probability of problem being solved equal to 0.72. Fine? Okay. Let me clear this. Next problem. Here is the problem. A pair of fair dice are rolled until sum of dice 5 or 7 appears. So that the probability of 5 appears before 7 is 2 by 5. Okay. Here the experiment is we keep rolling pair of dice until we see sum of the dice 5 or 7 appears. Okay. So here we need to show that the probability of 5 appears before 7 is 2 by 5. So here our experiment may terminate due to sum of the dice 5 or sum of the dice 7. Here we need to show that probability of our experiment terminating due to sum 5 is 2 by 5. Okay. Let's define few events here. Let AI be the event that either 5 or 7 appears on ith trial. See, on any trial, we are rolling pair of dice, right? Okay. There will be 36 possible outcomes in which 4 will be favorable to getting sum 5. 1, 4, 4, 1, 2, 3, 3, 2. These 4 are favorable for getting sum 5. And 6 outcomes will be favorable for getting sum 7. 1, 6, 6, 1, 5, 2, 2, 5, 4, 3, 3, 4. Okay. So there will be total 10 outcomes favorable for getting sum 5 or 7, and there is no overlapping here. So the probability of AI going to be 10 by 36, okay, which is same as 5 by 18 for any I equal to 1, 2, 3, so on. Okay. Let BI be the event that 5 appears on ith trial. Okay. On any trial, I told you that there will be 4 outcomes favorable for getting sum 5. So the probability of BI is going to be 4 by 36, which is 1 by 9 for I equal to 1, 2, so on. Okay. Now, let En be the event that no 5 or 7 appears in first n-1 trials and 5 appears on nth trial. Okay. Here En denote the event that seeing sum of the dice 5 first time on nth trial before sum 7. Okay. Now this En can be expressed in terms of AIs and BIs like this. Okay. This En we can express like this. Intersection I equal to 1 to n-1 AI complement intersection Bn. That means A1 complement intersection, A2 complement intersection, A3 complement intersection, so on, An-1 complement intersection Bn. That means A1 complement happened means no 5 or 7 on first trial. A1 means 5 or 7 on first trial, right? A1 complement means no 5 or 7 on first trial, no 5 or 7 on second trial, no 5 or 7 on third trial, so on, no 5 or 7 on n-1 trial, and Bn means appears 5 on nth trial. Okay, this is precisely we mean by En. So that's why we express En like this. Now the probability of En going to be the probability of the right hand side. Now the probability of the right hand side intersection going to be product of the probabilities. The reason is A1 complement is event associated with the first trial, A2 complement is event associated with the second trial, so on. An-1 complement is event associated with n-1 trial, and Bn is the event associated with nth trial. Okay, and all these trials are independent. That means result of one trial will have no effect on result of any other trial. So all these trials are independent. Any events associated with the independent trials are also going to be independent. That's why we can assume that this a1 complement, a2 complement, so on, an minus 1 complement and bn are independent events. That's why the probability of this intersection going to be product of the probabilities. Now we know that probability of ai is 5 by 18. So probability of ai complement going to be 1 minus 5 by 18, which is going to be 13 by 18. Anyway, let's write it. The product I equal to 1 to n minus 1. The probability of ai complement is 1 minus 5 by 18 and probability of bn is 1 by 9. Okay. Now this whole thing gets simplified to 13 by 18 to the power of n minus 1 times 1 by 9. Okay, this is the probability of en for any n equal to 1, 2, 3, so on, for all n. Okay, now we can also see that this e1, e2, so on, en are mutually exclusive. Okay, we don't see two happening simultaneously. Okay, at most one will happen. Just you can verify. Now, our event of interest, 5 appears before 7, can be expressed in terms of this E1, E2, E3, so on, like this. Union n equal to 1 to infinity En means what? At least one of EI happening, right? Okay, that means seeing some 5 first time before 7 on any track. So it may happen on any track. Okay, so that's what we mean by 5 appears before 7 means, see, that means seeing some 5 first time before 7 may happen on any track. That means E1 may happen or E2 may happen, so on. That's why, so this 5 appears before 7 event can be expressed as a countable union of these ENs, union n equal to 1 to infinity En, because it may happen on any track, right? So fine. Now we are interested in probability of this union. Okay, so the probability of union of these En is going to be sum of the probabilities, because we realize that these events are mutually exclusive. So we can use axiom 3. Probability of this union going to be sum of these probabilities. Summation n equal to 1 to infinity probability of En. And we already know probability of En. The probability of En is what? 13 by 18 power n minus 1 times 1 by 9. So let's plug it here. Summation n equal to 1 to infinity 13 by 18 to the power of n minus 1, 1 by 9. Now if you take 1 by 9 common, then it will be 1 plus 13 by 18 plus 13 by 18 square plus 13 by 18 cube and so on. You should know that there is a geometric series 1 plus x square plus x cube and so on. This series will be convergent when mod x less than 1, 13 by 18 anyway less than 1. So the sum will be 1 by 1 minus x. That's why after taking this 1 by 9 common, so this will be equal to 1 by 9 times 1 by 1 minus 13 by 18. Okay, now this is equal to what? 1 by 9 will be 18 by 5. Okay, this 9, 2 gone, so you end up with 2 by 5. So therefore the probability of 5 appears before 7 equal to 2 by 5. Fine. Okay, let me stop now. Thank you.